Hi, and welcome to this tutorial on using CapExt for virtual prototyping of capacitive touch sensing in 3D designs. We are going to cover the entire workflow from design considerations in the CAD tool to export to STL, and then import configuration and simulation of the 3D prototype in CapExt. Here I am showing you an automotive door handle design done in Blender. This isn't how door handles are constructed, but it still serves as a good example of a double-sided touch design. Meaning, that there are touch sensors on both sides of the PCB. One to lock the car by touching the lock button, and here, one to unlock as you grab the inside of the handle. Now, Blender is likely not your preferred CAD design tool, but the process that I use to import the model into CapExt is pretty much the same. One thing that's going to ease the import of the model is that you add the PCB outline to your design. If your official design files cannot have this, make a copy where this is added. You will soon understand why. Here, the PCB has been added as a part of the structure. This is a simplified model where the entire volume of the door handle is filled with a non-conductive material. Hence, the PCB has contact with the door handle material everywhere. Normally, that's not the case, but for this demonstration, it makes no difference. CapExt imports 3D models as STL files. Make sure the resolution of your model is limited. Remove all heavy interpolation subdivisions to reduce the number of polygons for CapExt to process. If not, your model may not import. In Blender, this is done by making sure you export the model without the subdivision visible and before it is added as a permanent modifier. If your CAD tool has the option of permanently adding subdivisions, you need to branch off a 3D model for CapExt before this operation is carried out. Okay, let's export our STL file. There we go. And now let's look at our PCB design. The board has been designed in Altium Circuit Maker and contains one mutual capacitive sensor for the lock button. We have 5 interleaved electrodes, 2X and 3Y. The unlock button covers the entire free surface of the board's backside. Here we have made 6 interleaved electrodes, 3X and 3Y. These are made thin to reduce the default capacitance. And now, let's fire up CapExt and build our virtual prototype. Let's start a new project and import the PCB gerbers first. This is a 2-layer design, and depending on what layout tool you are using, your files may have different file extensions. The minimum required layers are the top and bottom layers. These define the copper layout, as well as the drill foil, which contains information on the location of the vias. The via locations are needed for CapEx to understand where tracks or electrodes on the various layers are connected. The 4th layer we import is the keep out layer, which defines the dimensions of the board. If omitted, CapEx will still work, but it will crop the virtual prototype board to fit the contents. This means that the unused areas may be reduced in size, or that silk screen contents outside the board may cause the board to grow in size. It is therefore advised that you generate and import this layer. We also import the top and bottom overlay layers, which contain the silk screen layout. These layers are purely optional and have no influence on the results, but they contain information that may be valuable when setting up the measurements and evaluating the results. So we'll import these layers, and when asked, we will confirm CapEx predictions as to what is what. We will just use the default settings here since they will work well for our project, and click OK. And here's our board. If we zoom in and rotate it, we can see that the vias are connecting the two layers like they should, and everything basically, looks okay. Before we import our 3D model, we'll go ahead and identify and name the electrodes of interest. This can be done with the 3D model imported, but it is somewhat easier to do it at this stage. To do this, we click Simulation Options, and here we get a long list of electrodes. Now, CapExt doesn't know which PCB track or which isolated piece of copper makes up an electrode. So it just goes ahead, finds all the isolated pieces, calls them electrodes, and give them a number. And in order to identify which ones are what here, we have to mouse over. So for example, here, we see that this one with the three Y electrodes connected for the unlock, we see that that is electrode number 10. So we click that. Now we have identified that we've selected that electrode number 10 should be a part of the virtual prototype simulation. Now we go on the next one, which is this one, which is the X electrode for unlocked. And we go ahead and we click that. And also at this point, we're going to rename these. So we call this one locked underscore, lock underscore X. And this one we call locked unlocked underscore Y, and unlock underscore X, like that. The one reason for renaming the electrodes is obviously that it's easy to understand what is what, but it also makes it possible to filter out all the electrodes that we're not going to be using, that aren't really electrodes. Then we go here and we find these two. If I click on those, that's electrode 1. We call that lock X. And these three guys here, we go ahead and we rename to locked Y. And now if we click hide electrodes with default names, we're left with the touch electrodes on the board, and it's much easier to manage the whole list of electrodes now that we've taken out all the names that we're not interested in. And then it's time to import the 3D model. Before we load our 3D model, let's save the project. And you will understand later why I want you to do this. So we save the project as tutorial 1. In this case, and then we go ahead and import the 3D model. To do that, we click Use 3D Model, and then we right-click in this field and select Import 3D Model. From here, we need to find our STL file and open it. Now, the STL file scales different from different CAD programs. We know that with Blender, we need to put in a scaling factor of 1000 for it to scale correctly. Other CAD programs may have different scaling factors. If you import your model and you cannot see it, there's a chance that your scaling factor is just too small and you have to zoom in really far to find it. So this is a setting that you will have to play around with a little bit until you found what works for your CAD program. We click OK, and here is our door handle. It's not in the right place, so that has to be fixed. But before we do that, let's take a look at it. It's a little difficult to rotate because the CapExt rotates around the PCB. But here, that would be easier once we get it in place. And here it is. One thing that's obvious is that the lock button is in the wrong place. The door handle seems to be mirrored along this axis. So with the lock button being on this side, that's not going to work. So before we do anything here, we need to import this again and invert it along, let's see, what axis we put on the axis here. And we see that, yes, it has to be inverted along the y-axis. So let's just click File, Open, Reset, and reload our project, and then start again to import the model. This time, we import 3D model, we find the STL file, and then we set scaling factor of 1000, and now we select mirror along y-axis. And now we can see that the lock button is indeed in the right place. Okay, this is good. One important thing to note is that all models imported into CapExt import as a hierarchy. We have a main body with some attached submodels, and this can be visible when I mouse over the different models here. For example, we can see that, and the easiest way to do this is to click visible and physical. We see that this tab, for example, here is a different submodel, as is this tab, as is the PCB inside here. Since this door handle is made of plastic, it is important that we also select the right permittivity, and that we do by the same way that you do any layer in CapExt. You click this box and you select plastic, and this gives us a permittivity of 3.4, and the default is that all the submodels inherit this setting. So that is important in order for us to get the properties of the door handle correctly when we do the simulations. Let's rotate the whole thing so that the PCB is oriented the right way. Obviously, the door handle is 90 degrees rotated around the z-axis. So if I now click rotate manually, I get a number of options to rotate the model. One thing that you see is this rotate wheel, three-dimensional rotate wheel, that can be used to rotate the model freehand, but we don't need to do that because everything here is in 90-degree angles. If I now click the Z, rotate 90 degrees, I see that I get the handle aligned with the PCB. But obviously, the lock button here is on the overside here, and then it's on the underside of the PCB. So we need to also rotate the door handle 180 degrees around the x-axis. And that would do by clicking twice here. And now it seems to be in place. Still not aligned, but that will fix in the next steps. So we'll leave rotation mode now that this has rotated correctly. And now I go into this menu and uncheck physical and visible to get the main structure out of the way while we align the PCB. Okay, it is always easier to move the PCB in one plane at a time. So the first thing we do is to select view direction from the top. And then we click 2D view. So that gets rid of any perspective, which just makes this more difficult. And if I try to move the model, it's not going to be moving because it says 3D objects are locked. So I need to unlock the 3D objects first and then go in and move it and try to move it as accurately into the PCB as possible. If I zoom in and pan over a little bit, it should be easier to see that if it is aligned properly. There we go. That looks pretty good. Now I go back here and I look at what it is in the Y direction from the side. Okay, we can see that it's not properly aligned in. I didn't do a good enough job on the from the top view anyway, but now it looks. Hold on, let's move. We can scroll that a little bit and move to the end here. Says that I have a little shorter PCB than I should have had. But yeah, this is just my design that is a little sloppy. I put in some wrong numbers. So, but if you do this correctly, it's not a problem. And then we go and look in the, and it doesn't affect the simulations a lot either, but that's a little sloppy on our part. Now we go view from the X direction, and we zoom in, and we see that there's a little bit of misalignment here. The board width, at least, is really accurate. So go back to Y, looks good, and from the top, looks good. Okay, that means that we're now properly aligned. And if we turn now the visibility and the presence of the door handle main structure back, and go to 3D view, we'll now see that, yes, the lock button grooves align nicely with the sensor on the inside. So this is all good. And now that this is in place, we lock 3D objects. And that means that if I now start driving here, it's not going to move the model relative to the PCB. Very good. So with that, we have set the permittivity right. We have locked the object in place. There's one last step that's easy to forget, and it's going to be very hard to debug later on. Remember that we have a plastic PCB block here that was generated in the CAD tool. That now overlaps completely with the PCB that CapExt has generated in the virtual prototype. So two PCBs are occupying the same space. That is going to give weird results because the materials property will not be correct when you have two overlapping objects. So if we go back and we look at the list of 3D models here and we mouse over the hierarchy, we'll see that once we get to model 4, that gets highlighted as our PCB structure. If I now uncheck visible and physical, it gets removed. Well, it is still there, but CapExt will disregard it and we cannot even see it. And that will yield correct results for our simulations, which is the next thing we will do. The most valuable simulations in the virtual prototyping that CapExt offers is what is known as area touch. Area touch tests multiple points in a grid on the entire touch surface that you specify and shows you how the sensitivity varies. So in order to do that, we have to enable the touch probe and we have to enable area touch. And this provides a grid on the overside of the PCB, which is actually the underside of our design, but we can rotate everything to see that how this works and get it in place. The surface that is touched by the hand grabbing the door handle is what is important to us. The touch grid is always rectangular, so we can move it a little bit, and then we can make it wider as in order to cover a larger area. And this will now we do by finding the touch surface size parameters. And well, let's bring the width up to 24. So this will give us a better coverage of this area. It probably should be good enough. Now we can see that this grid currently sits on the PCB and not on the door handle itself. And we click Apply Changes. This will correct that. And it will build a project where we can see that this is now mapped to the surface. At the ends here, we get some artifacts because the grid gets stretched, but this is an uninteresting area to us anyway, so it doesn't really bother us. Then it's time to do some simulations. Let's go into simulation options first. Here we see the 4 electrodes that we identified earlier in the tutorial. We have lock X and lock Y, which make up the lock sensor or lock button. And then we have unlock X and unlock Y, which make up the unlock sensor on the inside of the door handle. Since these are to be viewed as 2 mutual capacitance sensors, we don't need to simulate all of them. When you simulate log X, CapExt finds the capacitance between log X and every other electrode on the board. And conversely, with log Y, you find the capacitance between log Y and every other electrode on the board. It also does self-capacitance, actually. Now, the lock sensor is the touch sensing circuit measuring the capacitance change between lock X and lock Y. So we don't have to do both of them. Lock X versus lock Y and lock Y versus lock X is exactly the same result. So the Y electrodes we can take out since they're not going to provide any additional information and just add to our simulation time. So now that we've concentrated on lock X and unlock X, we go to simulation. We start the simulation. But the first thing we do is that we go for, let's say, 10 minutes total. We're not going to use that time, but we set up a time and go for an accuracy of 2%. What CapExt now does is that if it gets the accuracy down to 2%, it stops the simulations. If it doesn't get down to 2%, it stops after 10 minutes. But CapExt is so fast, even on a less powerful laptop, that this is not going to be a problem at all. So we click Run Simulation. And here we start out simulating sensor number 1. It's already down to 2%-ish, and there it's done. And now it does simulation number 2. This one takes a little longer time because we have longer electrodes and we have more of them. So it's a little more complex sensor to simulate, but still getting now down to about 2%. And when it's done, we can start viewing the results. Let's select simulation results. And since I want to look at the lock button first, let's rotate the design so that we can see the door handle in the right place, and click touch on the reverse side to view what is going on here. And if we then expand on the lock itself, lock X list of results, it's really messy. There's a lot of stuff here. So if we hide the electrodes with default names, it gets a lot more manageable. So lock X obviously has some self-capacitance and has then coupling with all these other sensors. And the one we're interested in coupling with lock Y. Now, it's a little messy here. It looks like it's incredibly sensitive around here, this area, and also quite sensitive over here, way outside the button. And this is because the scaling is off. And this sometimes happens when we rotate a design. So if I now press rescale from view, we get a much cleaner picture. And we see a very nice touch response. Let me zoom in a little bit on this. We see that the touch response in the middle is really high, where you expect to put a finger and it trails off, and outside there's almost nothing. And what's also important here that on the underside there should be almost nothing, and there isn't. So this is looking really good. This is what we expect, and means that there's a good chance that this is a design that's going to work. Now, if we go and look at, let's turn this around, we'll look on the underside where the unlock button is. We go to unlock XL versus unlock X versus unlock Y. Again, we need to rescale. And we see that we're really nice response, a little stronger here than over here, but sufficient enough to register a touch no matter where on the underside you put your hand. And if we go and look on the overside, there's a little bit of response here, but it's easy to tune this so that it doesn't affect the touching on this side, which would be an unintentional touch. Now, in the real world, there will be an air gap between the board and the plastic at this point, so it will be completely off. But in a normal door handle, that would be the case. But here, for simplicity, we just fill the whole thing with plastic, and this is what we get. But it means that even with this suboptimal mechanical design, we're going to be able to distinguish between a touch on this side and a touch on this side of the PCB. So that all looks good, and with us being satisfied with the results, that completes the tutorial on how to import a 3D model with a two-sided touch board and simulate and get results that tell you how robust and how sensitive your design is going to be in the real world. Thank you for watching.